So, how do TRN inhibitor spikes place a frequency modulation on pyramidal neuron outputs? Well, the detailed properties of the synapses made by the TRN play a significant role. TRN outputs are GABAergic, and GABAergic synapses onto pyramidal neurons are known to sometimes be located close to excitatory synapses, sometimes at the junctions of branches, sometimes on the stem of the dendrite, sometimes on the soma, and sometimes even on the initial segment of the axon emerging from the target neuron. Now, I've been calling GABA synapses inhibitory, and predominantly they are. But depending on the relative timing of excitatory and inhibitory inputs, an inhibitory input can sometimes have a net excitatory effect. And the relative location of the two synapses can also be a factor. It will affect the timing, for example. But for simplicity, I'll leave that consideration out. If the GABAergic action potential arrives later than the excitatory input, it's inhibitory. It'll reduce the effect of the earlier excitatory input. If it arrives a little bit after, it's also inhibitory. If it arrives just before, it's still inhibitory. But if it arrives more than about 5.5 milliseconds earlier than the excitatory input, it's actually excitatory, and it reinforces the effect of the later excitatory spike. So, in the absence of a modulation signal, the postsynaptic potentials are randomly distributed in time. The peak dendritic potential, and therefore the most probable time for neuron firing, could occur at any time. In this specific case, let's suppose that most probable time is here. Now, suppose a spike arrives from a TRN neuron, and it arrives at the same time close to all these excitatory synapses. In the top case, it arrives more than 5 milliseconds before, so it increases the postsynaptic potential. In the second case, it arrives after and decreases the potential. In the third case, it arrives just before and decreases. And in the bottom case, it arrives significantly before and increases it. So the peak total synaptic potential has therefore been shifted to tend to be more than 5.5 milliseconds after the GABAergic spikes. In other words, outputs from the target neuron will tend to be at the same frequency as the GABAergic inputs, but out of phase by about 5 milliseconds. Fine, now that's okay, but how can a GABAergic synapse be both inhibitory and excitatory? And we'll have a look at that in the next section.